So in this presentation I'm going to prove the Heine-Borel theorem that is stated as follows. A subset S of the set of real numbers is closed and bounded if and only if S is a compact set. That is, every open cover of S contains a finite subcover of S. So the proof consists of three parts. First I'm going to prove that if S is compact, then S is bounded. Then if S is compact, then S is closed, and finally, assuming that S is closed and bounded, then S is a compact set. So the first part. Suppose that S is a compact set. Let's prove that S is bounded. So we're going to construct a fairly simple open cover of S. So for every natural n, we can consider an interval in, an open interval, from -n to n. So clearly, if you take a union of these intervals, then we've got the whole set of real numbers, and since R contains S as a subset, then this collection In will be an open cover. So therefore, this collection In is an open cover of S. Since S is a compact set, okay, we can find a finite subcollection that is also an open cover of S. So we can find some subcollection, say I n 1, so on, I n k, okay, so that S is contained in the union of these k intervals. Okay, but we know that for every I less than or equal to j, I is contained in ij. So if you take the maximum of these k numbers, the maximum of course exists, and denoted by m, then as you can see, for every n I and I will be contained in the interval im. Okay, so therefore the whole union of these k intervals is contained in the interval im. Okay, so therefore S is contained in the interval im. Okay, and therefore for every element of S, we have that x lies in between -m and m. So we found a lower bound -m and an upper bound m. So therefore is a bounded set. Okay, so we need just present one upper bound and one lower bound. Alright, so the next step is to prove that if S is a compact set, then S is a closed set. So let me proceed as follows. So let's suppose that S is not closed. So in this case, we have at least one point, a point of closure P, that doesn't belong to S. So we can find at least one point from the difference, the closure of S minus S. Okay. So now for each natural n, again we can construct an open interval In of the following form. It will be an open interval around P of radius 1 over n. So it's P minus 1 over n, P plus 1 over n. Okay, and then In bar will denote its closure, so it will be a closed interval. Okay, and finally we can construct a set Un as the complement of In bar, so it will be R minus In bar. Okay, and then as you know, a set is open if and only if its complement is closed, and vice versa. So In bar is definitely a closed set. So therefore its complement UN is an open set. Okay. Now what happens if you take the union? So if you take the union of all these intervals, okay, actually all these sets UN, and then the use, what we can use? We can use actually the De Morgan rule. So it will be union of what? Of the complements R minus IN bar for all natural n, and then again according to the De Morgan rule we have it's a difference R minus the intersection of the closed intervals. So now if you think about these closed intervals and what we have in the intersection of all of them, clearly the only point that is contained in that intersection is the point P. Okay, so we have that R minus the point P. Okay, so now what we know? We know that P doesn't belong to S, okay, because it was selected as a point of closure that is not a point of S. Okay, so therefore, okay, that difference R minus P contains all points of S. Okay, so therefore, again by definition, since that difference is nothing more but the union of sets UN, we have that this collection UN is an open cover of S. Since it's open cover, and then since S is a compact set, we can select, we can find a finite subcollection. Okay, so again we have a finite subcollection of the sets UN1, UNK, okay, such that its union of all these sets contains S. Alright, so now what we can observe? We can observe that actually for every n less than k, we have that interval IN actually contains interval IK. So therefore, and the same true is for the closures. So therefore, the complement UN is contained in UK. Okay, so that's what we observe. Okay, so again, if you take the maximum M of these K indices, we have that element UM actually contains all these subsets. Okay, so therefore, and also UM is a part of that collection, of course. So therefore, we then take the union of these sets. We obtain nothing more but the set UM, which contains S. Okay. So that doesn't mean. It means that the intersection. It means that the intersection of S and the closed interval IM bar is actually empty. Okay. So that, what does it mean? It means that actually for that we found delta. So we found delta, and that delta will be 1 over m, so that the intersection of this interval P minus delta, P plus delta with S is empty. But the point is that this contradicts that P is a point of closure. The P is a point of closure of S. Okay, so that concludes the proof of the second part.